Hey everybody, you'll take a look at the two little trig equations that I've written in white on the screen. What I want to do is go through how to solve those two small little trig equations using rotation angles or using a trig curve. And what we're going to talk about are ones that are not limited to one rotation only. So we're going to solve for some general statements, that is, the infinitely many solutions that could arise. Okay, let's jump in. So let's take a look at the first equation. Tan x equals negative 1 over root 3. Now, this is one where if you really know your tan curve super well, I'd probably just use my curve. But probably like most, your sine curve and your cos curve are better known, your tan curve less. So if I were you, my suggestion would be, let's go back to rotation angles. My tan is negative. That means my opposite and my adjacent sides are different signs. So I am in quadrant 2 or 4. So now what that means is if I was to drop in my altitudes, my opposite side and my adjacent sides are like that. And then we could draw the conclusion as I zoom in to write in. I have a small opposite side, which means I have a small special angle. And we know that that related acute angle is pi by 6. So if you were to then give that solution, you could end up writing that therefore x is going to equal a 5 pi by 6 in quadrant 2 or an 11 pi by 6 in quadrant 4. But you'll notice what you just wrote in gold implies that there is only one positive rotation, and that restriction has not been given in the problem. So if I was to then shorten it up a little bit, and I could say that my quadrant 2 answer would come up 5 pi by 6 plus any full rotation in either direction. If we imply then that k is an integer, then that plus 2k pi would give me any full rotation. I could then write that I was at 11 pi by 6 plus 2k pi with that same restriction on k, that it is an integer. But you'll notice that I don't require those two statements. If I go back to my diagram, you'll notice that whatever this rotation is that takes me from quadrant 2 to quadrant 4 is the exact same amount as takes me from quadrant 4 to quadrant 2. And that those two rotations are not a full rotation apart, but a half of a rotation apart. Which means I don't need to rotate 2k pi, I could just rotate k pi, any pi units. And I would end up landing in quadrant 2 or quadrant 4 on that exact same terminal arm. So what I can do is I can condense my statements then to, rather than saying I have to go 5 pi by 6 plus a full rotation, then 11 pi plus a full I could shorten it up to that one statement as long as k is an integer. Now, we won't require your statement for k is an integer as long as we all know that whenever we use the value of k, we mean an integer. That's a class rule for us. Okay, there we go. That would be your one statement that would incorporate all possible angles. You could, of course, written down 11 pi by 6 plus k pi, and that would have been just as good. Okay, let's jump over into question B. Well, I know my cos graph pretty well, and I want to highlight that you've been given a special value for cos. Anytime I've been given a max, a 0, or a min, I want to use my cos curve because I know it well enough. So what I can do is I can picture my cos graph, and I know that my cos curve starts at the top and falls. Okay, so when do I hit up a value of 0? Well, I noticed that I hit a value of 0 at those two blue locations. Okay, my coast curve starts at the top and falls, and I hit my 0 at pi by 2, and I hit my 0 coming back up again at 3 pi by 2. And so what I notice in that case then is I could say the same thing as the last, that my x is going to equal pi by 2 plus a 2k pi, and I could think about it as the full rotation again. I'm falling to 0 every full rotation before or after pi by 2. And then do the same thing with a 3 pi by 2, except I notice I can condense that statement. That pi by 2 and 3 pi by 2 are pi units apart. And my curve, if I were to continue it, would hit my 0 another pi units from that. And so I could now have a condensed statement of a k pi with the same restriction on k. As long as k is an integer, I will always hit a 0 at those x values. Okay, there's two examples. One on the left, where I used rotation angles. One on the right, where I would use my curve. What I want to do now is I just want to jump into one more so that I don't put an idea in your head about the whole k pi thing. Okay, let's jump into the next one. So let's take a look at C. C is another case where I'm talking about a sine, and I notice that what I have on the right, when you take a look, that is another special value. That's the minimum of my sine curve. So as I'm working my way through on that one, I want to picture my sine graph, and I know that my sine curve starts in the middle and rises. I notice that I hit that value of -1 down here, and we should be pretty familiar that that would be at a value of 3 pi by 2. So if I had to think about that statement, I'm then going to state, well, therefore, my x is going to have a value of -1 at 3 pi by 2, but since there's no restriction on x, I need to include all possible values, and you will notice that we are going to hit that 3 pi by 2 before or after, sorry, we're going to hit -1 before or after 3 pi by 2 every full rotation, every 2 pi. And so my statement for that equation would then be plus my 2k pi to incorporate that interval. Okay, I'm hoping that that gives you a few examples of when to use rotation angles and when to use your curves. Okay, jump in, play around with your practice. I hope that helps you out.